Hey, you guys. Well, I wanted to go ahead and keep on working on chapter 7. We're going to look at sections 7.4 through 5 in this slides show. And we are still in quantum theory and the electronic structure of atoms. We've gone through some questions, and those questions are, what is light? And that was kind of in the beginning, couple, 2, 3 sections of this chapter. And it's energy, right? Light is a form of energy in the form of photons of light, which we learned about. How does it travel, right? It travels as waves and particles. Bohr was studying that, as well as, it was his name, Planck, yes, was studying that as well. Waves, particles, Einstein was looking at that with the photoelectric effect. So looking at how fast does it travel? Remember the formula that we used for that, how the speed of light in a vacuum was related to its frequency and its wavelength. Here's our wavelength, and here's our frequency. We talked about what is the energy of light, and that's where Planck's theory came in. Of energy of a photon of light was related to Planck's constant and the frequency of that light, or wavelength, remember, since they are related. So that was Planck's theory of light. What was light's behavior? If you remember, we went into the photoelectric effect, and the photoelectric effect, Einstein was talking about that light caused the ejection of electron. So it has a certain behavior like a particle, and that's why it could eject an electron from that metal. Where is the electron? Remember how I showed you this GIF up top here? If you look up in the upper left of your screen, you'll see that GIF that we looked at in a previous slideshow, and it was showing how light causes the production or promotion of electrons from one level to another. And Bohr thought that that's the reason why the line spectra was created, is because as those electrons fell back down to their energy levels that they were in previously in the ground state, that bit of energy was given off, and that bit of energy could be captured on a piece of film or through a spectroscope, and you would see certain lines. So where is an electron in an atom? It's in certain, or call it orbits, right, that surrounded the nucleus. What is the energy of an electron? And then Bohr used that information to say that the energy of an electron is related to that Rydberg constant. I remember the RH. And then the electron, depending on where it was, that n value, and 1 over n squared, that n value is how far it was from the nucleus. So here was 1, here was 2, and then here was 3, and so on. So that is what Bohr came up with as far as the energy of an electron in those orbits. So now we're going to look at how does an electron move in an atom. And there's a couple of different, we're also going to look at some more topics there, but there's the quick recap of what we've covered so far in chapter 7. And then now, how does an electron move? Because up in this GIF, it doesn't really show how that's moving. It's just saying where it is and then what it's doing, that it gets promoted and then it falls back down and gives off energy that it absorbed. So let's look at this next section here, the dual nature of the electron. Why is the energy of an electron in an atom quantized? Now, this was kind of weird because Bohr said, well, it can only be in certain spots. It can't be in between. So that, here's the nucleus. If you look at my drawing up here in the upper right-hand corner, it could only be in certain orbits, and that means quantized, only in certain distances from the nucleus. So de Broglie reasoned that the electron is both wave and particle. So what does that mean? He reasoned that because if it is moving as a wave, it can only be in certain distances from the nucleus, because that area, it's restricted and its location is tied to its wavelength. And then its wavelength is tied to its location. It's like they depend upon each other. So if it's traveling like a standing wave, your book talks about a standing wave, and that wavelength is dependent on its orbit. Now I have a GIF coming up here that's going to show you what a standing wave might kind of look like in a circular orbit. So it's combining the orbit and the wave nature. So if it's traveling, it's not really traveling, it's moving as a standing wave, that wavelength must be dependent upon the size of its orbit. For example, here's an orbit. Think of this being laid on its side, and this is kind of like a three-dimensional thing here. There's certain size orbits, and that electron, if it's moving in here, can only fit a certain wavelength in that, and that wavelength is dependent upon which orbit it's in. So what de Broglie reasoned, and using the circumference of a circle, he kind of combined these two ideas, and there's the gift that I was talking about, is that the electron is moving in a wave fashion, and the number of nodes, if you count this, your book talks about nodes, you can count the number of nodes in this orbit, and that number of nodes is dependent upon how big that orbit is and what wavelength can fit into it. So what de Broglie did was thinking about the circumference of a circle, which is like an orbit, and how many wavelengths, see here's a wavelength, lambda, can fit into an orbit of n value. Now the n values that we have are n equal 1, look up in the upper right corner, n equal 2, n equal 3. And those orbits then give that wavelength value. That is the circumference of a circle. And this r is called the Bohr radius, and it was actually calculated based upon a number of parameters. That's kind of the radius of where these are. Look on the upper right again. There's that radius as you go out. Those are the Bohr radii for each one of those. So this wavelength, what de Broglie was saying then, is if an electron can act as a wave, it has a mass, it has a speed, and it has Planck's constant because it's on that level of smallness. And that's why Planck's constant is included. So this velocity of the electron, if something has a speed, it has a wavelength. Now, if it's a very tiny particle, that wavelength is actually large enough that it can be measured. If it's a huge particle, like a bird or a ball, then that wavelength can be calculated, but it can't really be measured. And so does that beg the question, is it really there? I don't know, but we can definitely measure the wavelengths of these subatomic particles. So thinking about the wave particle nature of an electron, if the idea of something being a wave, when something is a wave, it diffracts, and it diffracts through a prism. So when you have something that's acting as a wave, it will diffract. So X-rays were waves, they were electromagnetic radiation. And when they were put through aluminum foil, a very thin layer of aluminum foil, you would get diffraction. Now remember what aluminum foil is. Aluminum foil is a layer of atoms. So if you make it really thin, you're going to have spacing between those atoms. And those spacing between those atoms is like a diffraction grating. So when you then put something through it, it hits one of those and it diffracts. Comes through and hits that and diffracts. So then you get these circles. So this circle picture looks more like dropping a stone in a pond, and then you get those radiating waves. But you get the same idea when you pass light through a very thin layer of a metal, just like Rutherford did when he was passing alpha particles through gold foil. And they diffracted, right? And they diffracted mainly because hitting the nucleus of an atom, but what was he passing through? Huge alpha particles, which are 4 subatomic particles, so they're pretty big. This, however, is electromagnetic radiation, which doesn't have that mass to it, so it wouldn't bounce off the nucleus like Rutherford's experiment, but if there is spacing between these atoms, that is like a diffraction grating, just like down here on your prism. So what they did then is said, well, let's pass electrons. We can create a beam of electrons and pass them through foil. And sure enough, you saw these circles. And that circles means something is traveling in a wave-like fashion. So why it's traveling in the waves? This was like, what? What is that? That's not supposed to do that. It's a particle. So it's supposed to just pass through, and you would just end up with a bunch of particles coming through, and you get an exposure like this. But that was not the case. This was the evidence that electrons were behaving as waves. So let's look at de Broglie's equation, and how we could apply it to anything traveling at a certain speed. So in this example, as far as a wavelength of a ping pong ball, if it has a mass and it has a speed, you can calculate its wave length. Now, of course, this h is Planck's constant, and that's going to make everything really, really small. And that's why when something is really, really small, like an electron or a proton or something teeny tiny, and it's moving very, very fast, that it will then have a measurable wavelength. So let's look at this one, though, as far as a ping pong ball is concerned. H is Planck's constant, and that's in joule dot seconds. Mass has to be in kilograms and U has to be in meters per second. And that's because meters per second and kilograms are both included in the joule. And so there's a second in there. So we have to make sure to include that. We learned about the joule in chapter 6 and chapter 5, not chapter 5, chapter 6 when we were talking about thermochemistry and energy. So let's put all these numbers in here. Now this is a no-no, but I think they were taken out. So for clarity, a joule dot second, and this is a kilogram, and then this guy is a meter per second. And when you do your calculation for this and plug in all your numbers, you get 1.7 times 10 to the negative 23rd nanometers. Now it showed up in meters to begin with. This was in meters, and this is going to nanometers. And that is really, really, really tiny. And since that's so small, that it's not measurable, and therefore it's not observable to us. But that doesn't necessarily mean that it's not doing that. We might not just have the instrumentation for that yet. So on your fun sheet, for numbers 8 and 9, I ask you to use the same thing, Planck's formula, and Planck's formula, not Planck, I'm sorry, de Broglie. And de Broglie's formula was lambda equals h over mu, and we just use it for the ping pong ball. And then you could do that for each one of these. A thermal inert neutron, which is a tiny particle, moves slowly, I guess compared to what, and can initiate a nuclear chain reaction. So the goal is to calculate the wavelength if it's moving at 700 meters per second, which is the speed. So you'd have to look up the mass of a neutron and, of course, use Planck's constant. And you can do the same thing with the hummingbird. Now you should notice when you do this calculation that the hummingbird's wavelength is going to be very tiny compared to the wavelength of a subatomic particle like an electron or a neutron or a proton. Which is kind of weird because, but not really, because when you look at the formula, you'll notice that mass and speed are in there. So a bird is flying much slower and is much heavier. So then that makes your lambda much smaller. So go ahead and try those two problems and then compare the two different wavelengths, and you'll see that the subatomic particle has a larger wavelength, and it's more comparable to itself than the bird does. So in application, let's keep on talking about de Broglie's theory here and the subatomic particle having wave and particle nature, the electron having wave and particle nature, and the use of electron microscopy to visualize very tiny objects. So wave-like property of electrons can be used. Now, I don't know if the law of optics, this talks about this in your book in the Chemistry in Action, that it's impossible to form an image of an object that's smaller than half of the wavelength of light used for the observation. And that's kind of weird because you think, oh, here's a person. But if that gets really tiny, there's a dot. I just drew a dot. Here's a teeny tiny person. They're so small that they can't be seen by visible light. That means that visible light that is coming through there is too big. It's not hitting basically the little person, but it's hitting the big person. So that is why that it's impossible to form an image of an object that is smaller than half of the wavelength of the light used for the observation. What light is that? Well, you can use different types of light. You can use X-rays. You can use visible light. Now for us, it's visible light with our eyes. But let's talk about electrons. So visible. Let's finish up our visible here with our wavelengths. The wavelength, the shortest wavelength of visible radiation, is 4 times 10 to the negative 5th centimeters. So we can't see anything smaller than half of that using visible light. So a light microscope can only visualize something this small or larger. X-rays are even smaller. Their wavelength is 0.01 nanometers, but can't be focused. And it can't be focused because X-rays are not charged, whereas electrons can be focused because they are charged. So you can use magnets and electric fields and things like that to actually focus it. So as far as our wavelength of an electron here, that's what this is saying. That is the wavelength of an electron moving at a certain speed, and that's not indicated here. But you can see electrons, using electrons, you can see objects as small as 2 times 10 to the negative 10 centimeters. That's much smaller than using a light microscope. So this velocity of the electron determines its wavelength, which can be adjusted. And there's de Broglie's relationship again. De Broglie's relationship is based upon speed and mass. So if we say it's of an electron, If I put in a certain speed of that electron, and of course the mass is going to stay the same, and so is h, these are constants in this case, I can get a range of wavelengths that the electron can operate at, and then I can have a range of objects that I can see. So I have a picture here of a certain type of virus, I think this is. I'm not 100% sure. I have to look that one up again, but I think it's a certain type of virus. That can be, it's pretty big actually. You can see it with a light microscope. But if you use an electron microscope that's tuned to the wavelengths or the size of this substance, see it says 50 micrometers down here for this one, that's how the order of the magnitude of that particle that you want to be looking at, you can tweak your wavelength of your electron to that size, and then you can use it to see such tiny objects. I have another picture on here. I don't know if you can see it behind this. Let me hide this. These are called a water bear or these tardigrades or something. And this guy, he looks alive, but he's not. You know, as far as what I have learned about this electron microscopy, that the sample has to be frozen, and sometimes it has to be, the little object here has to be covered, or like kind of covered with metal. And that's because that metallic substance, metals have heavier, they have more electrons in their shells, and so they will interact with the electrons that are doing the probing more. So I did find some pictures where spiders and things like that were actually kind of covered with a metal so they could be visualized with electron microscopy. So anyway, pretty interesting stuff. And on your fun sheet, I have a problem like this for you to work on, which is right here. Here's a fun sheet question, which is talking about the electron microscope. And you can probe the matter or the arrangement of the atoms using the wavelength of the electrons. And the wavelength of the electrons depends upon the speed of the electron. So what this question is asking you to do is calculate the speed of the electron that is necessary to visualize a certain size of atoms. You know, this 3.32 nanometers is how far apart the atoms are. So what speed of electron would you need to tweak it to or tune it to so you could see it? So I'll let you guys work on that. That's number 10 on your fun sheet. So let's cover a little bit of quantum mechanics here. We're going to talk about wave nature of matter. Now, quantum mechanics, I think, also has wave particle nature of light and its wave nature, but it also then crosses over to matter and the particle and wave nature of electrons. So I have a little GIF going down here, and that GIF is showing you how waves interact with a double slit experiment. Now, this is a physics thing, and the double slit experiment was where waves were going, there's two slits here, there's the double slit, and as they pass through, they fan out. And since they fan out and they're moving in waves, they were moving in waves on this side too. But as they fanned out, then they started to interfere with each other, either constructively or destructively. So as they were moving, you would see constructive interference and destructive, and the destructive were these dark lines. And this is kind of evidence of the wave nature of something. This would be water waves. That's what this looks like. So the water is going through, and since it's traveling in waves, that liquid, that then you would get this destructive interference. At UCCS, they used to have this big, huge wave pool. There's kind of some neat things, some neat experiments that they have using this and illustrating the wave nature of a liquid. So let's go with quantum mechanics and the Heisenberg uncertainty principle. This is one of the sections out of your textbook, and his principle was it's impossible to know simultaneously the momentum and position of a particle with certainty. Okay, now that's because it's moving kind of like a wave. If a particle is moving like a wave, that's my next fill in here. No, that's one. This one is this uncertainty principle is this relationship. But before we talk about that, let's do some fill-ins here. If it is moving, it is wave-like. Okay, so when we have a particle moving, like whether it was the bird or the proton or the neutron, in those previous questions, if it was moving, it had wave nature. Remember, that was de Broglie's theory here. So we had H over mu. And it didn't say what it was. It didn't matter. If it was moving, it was wave-like. But if it slows down enough, it becomes more particle-like. Now, a particle has a speed and a momentum, and that's what this is talking about up here, this momentum, and then this is position. So as far as a wave, it's hard to say the position of a wave, and that's because a wave is like this whole medium down here, right? It's not like, where's the wave? Well, it's everywhere. Now I could say, well, where's the particle? That's a good question. So let's keep on going here. I think I have a couple more GIFs here to show you that might be helpful. The more you know about the position of something, the less you can know about its momentum. Because in observing its position, you alter its momentum. It's like you have to almost take a picture. You're like, look, I took a picture. There it is. Okay, but now I don't really know anything about its speed or its momentum. And that's what this is saying. The more you know about the momentum, the less you can know about the position. See, it's like vice versa. So in observing its momentum, you alter its position, almost because you have to hit it with something. You have to hit it with a photon of light or something to observe it. And in so doing, you alter its position. So I have another GIF down here showing the wave nature of an electron in an atom. And then I have another GIF down here that is showing kind of the electron as a particle. And you can see it kind of jumping all around. You don't really know where it is, but it's kind of everywhere at the same time. And it traces out a path of most likely where it's to be found. And the darker the areas, that's where it's most likely to be found. So this is the particle nature of something over here. This is the wave nature. Now in this GIF in the middle, this is like a wave pool, and a wave pool is for a liquid. But there have been experiments in which electrons have been put in this same type of arrangement. And that's what's on this next slide. Here's that same GIF that I was just showing you that was looking at the wave nature of like a liquid going through there and how it interferes with itself constructively and destructively. So you see lines over here. Now, if you have a particle, you might think, well, let's do the particle. Let's do it the same way. Let's do the same experiment. And if it's 100% particle, even if there were two slits, they would just pass through. And the ones that passed through would get to that spot, and they're on the opposite side of the two openings. So you do not see any of the bars like we do up here. But that wasn't observed. What was observed was interference patterns. And this GIF down here is the idea that if a particle, these are particles moving through, if they move through and they have wave nature, they interfere with each other. And by interfering with their wavelengths of each other, you get these dark light bands, which is just like the double slit experiment. So just like electrons were passed through aluminum foil and you got those circles, electrons were passed through this double slit experiment and you got interference patterns. And those interference patterns are evidence of wave nature of the particle. So quantum mechanics is a description of the wave nature of these particles and what you can actually know about them. So on our previous slide, we had that delta x, delta rho, greater than or equal to h over 4 pi. And that was an actual number. So there's like a certain limit of what you can observe about something that has wave and particle nature. And I have a video that is linked in your fun sheet, a Veritasium video that shows an actual experiment illustrating this particle and wave nature of light, because it was a slit experiment, and as a slit got smaller and smaller and light was going through it, you would think it would come out and just hit the other side. But what ended up happening, as this slit got smaller, the uncertainty in its position got larger, and you ended up with it kind of hitting, this actually got larger on the other side, the line. So take a peek at that video. I thought it did a really good job of showing an experiment of what this is all trying to tell you. So that's the end of this section's PowerPoint slide video, and that's over sections 4 and 5. So try your fun sheet over that and see if you can apply these formulas and understanding to those fun sheet questions.